Often different events are going to be sharing information between them. If we know that one event has happened, that's going to change our beliefs about another event. This happens very frequently, but it's also possible for us to imagine events that don't share any information between them. And when events do not share information between them, when our probabilities don't update, knowing that one thing has happened or another, then we refer to these as being independent events. So when events provide no useful information about one another, these are known as independent, statistically independent. So what is statistical independence? Well, intuitively, two events A and B are said to be independent if they provide no probabilistic information regarding one another. So for instance, we might look at rolling two dice, right? If I roll two dice separately, what happens with one die does not impact what happens with the other die. So they're independent. They don't influence each other. If you flip a coin and then you draw a card, right? If I flip the coin, get heads or tails, and then look at the card drawn from the deck, there's no information that knowing what happened on the coin flip is going to tell me anything about what's happened on the card draw. The number of questions answered correctly on an exam by two students who don't know each other, right? If I know how many questions one student answers correctly, that's not going to tell me anything about how many questions another student answered correctly, assuming that they do not actually know one another. Right? The intuition is that if our conditional probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B, then knowing one thing does not change our belief about the other. And so if we have that the conditional probability of A given B is equal to A, then if I tell you that B has happened, that has not changed your belief about the probability of A. And similarly, if we have that the probability of B given A is equal to the probability of B, well then if I tell you that B has happened, or that A has happened rather, that has not changed your probability about B. Okay? And so knowing one thing does not influence the other. So if A and B are independent, then we will write this as A and then the perpendicular sign and then B, right? So A perp B means that A is independent of B. And definitionally, what we use as our definition is that the probability of A and B has to be equal to the probability of A times the probability of B. So where is that definition coming from? So if we suppose that A and B are both positive probability events, right, and we write the probability of A and B is equal to the probability of A times B, then we can think about, well, what's the conditional probability of A given B? And by definition, that's the joint probability divided by the marginal probability. And so if they're independent, then the joint probability is probability of A times the probability of B, which then we can divide out the probability of B by the probability of B, and we're left with just the probability of A. And so intuitively, our definition here tells us that the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. So the intuition is telling us if the conditional probability equals the marginal probability, then they're independent. Formally, we define that through the joint probabilities. And so the definition actually says if A and B are independent, then their joint probabilities decomposed into the product of their marginals. Okay? So independence is defined by joint probabilities, but we sort of motivate it through conditional probabilities. Now note, if A is independent of B, then we also know that B is independent of A, and also A is going to be independent of B complement, A complement will be independent of B complement, A complement will be independent of B. Any of the different pairings there are also going to work. Okay, and so if you know independence between A and B, you know independence between all things related to A and B. So how do we go about using statistical independence? Well, if we can assume or infer that two things are independent, then working with our joint probabilities simplifies down to working with our marginal probabilities. So then knowing that probability of A and knowing the probability of B gives us the probability of A and B. We're not typically going to be verifying independence in practice, but often we will assume independence. Now, this might be able to be inferred through subject matter expertise, so there are certain situations where we can just know that things are independent. If we roll one die and then we roll a different die, those two things are not going to influence one another, right? So flipping two coins does not impact one another. But independence is not always going to be an appropriate assumption. And importantly, if you assume independence and it's not actually justified, if it's not actually valid, then the results that you get are going to be very misleading. And so independence needs to be justified. It comes up a lot. We're going to be making the assumption a lot because when we make it, it really simplifies working with our joint events. However, if you're assuming it and it's an invalid assumption, that's going to potentially very dramatically mislead the results that you get. So let's look at some examples then. Suppose that we have a card that's drawn from a standard deck of 52 cards. We take A to be the event that the card is an ace. We take H to be the event that the card is a heart, T to be the event that the card is a 10, and R to be the event that the card is red. And we want to know, is A independent of H? So is the probability, or is the event that a card is an ace independent of the event that the card is a heart, right? And so if A is independent of H, right, what does this actually mean for us? This would mean that the probability of A and H is equal to the probability of A times by the probability of H. Okay, and so then what we need to do is we need to work out, well, what's the probability, the joint probability, what are the two marginal probabilities, and do they actually multiply together? So how can you have A and H both happening? What is their joint probability? Well, you would need to get the ace of hearts, right? So there's a 1 in 52 chance that that happens, okay? And so then we want to know, is that equal to the probability that something is an ace? Well, there's 4 aces out of 52, so that's 4 out of 52. For our aces, times by the probability that something's a heart. Well, 1 in every 4 cards is a heart. So do we get 1 out of 52 is equal to 4 out of 52 times 1 over 4? Well, our 4's can cancel out here and we get 1 out of 52, right? And so yes, this does actually occur, right? And so then A is independent of H, right? So that's the general way that we're going to think about checking this. We look at the joint probability, we look at the marginal probabilities, and we see, does the relationship hold? So probability of A is 1 in 13, probability of H is 1 in 4. A intersect H is going to be only the ace of hearts, so that's 1 out of 52 for the joint probability. Probability of A and H is equal to the probability of A times the probability of H, so independence holds. Is A independent of T? Well, the probability of an ace is 1 in 13. The probability of a 10 is also 1 in 13. But what's the probability that you get an ace that is also a 10? Right? There's 0 probability of this. There are no cards that are both aces and 10s. And so because of that, we do not have that 1 over 13 times 1 over 13 equals 0. And as such, ace is not independent of 10. And this should make sense intuitively. Imagine that I pull open a card and I say, okay, this card is a 10. What is the probability that it's an ace? Well, that probability is now 0, right? Whereas before I've told you it's a 10, the probability that this is an ace is 1 in 13. So knowing that it's a 10 tells you a lot about whether it's an ace or not. Is ace independent of red? Well, we can work through this process rigorously again, right? The probability of an ace is 1 in 13. The probability that it's red is 1/2. Moreover, we have 2 red aces, and so that's going to be 2 out of 52, or 1 in 26. And so what we can do is we can check, is 1 over 13 times 1 over 2 equal to 1 over 26? It is, and so then A and R are independent. Is heart independent of red? Okay. So here, let's think about this sort of intuitively. If I tell you that a card's a heart, does that change your belief that it's red? And the answer is yes, right? And so we know that these two things should be independent. If the card, or that they should not be independent, rather. If a card is a heart, we know it's red, they cannot be independent. In fact, we could show that the probability of the heart and red is equal to simply the probability that it's a heart, which is not equal to the product of the probability it's a heart times the probability that it's red. Right? So we can check the definition directly there. We can consider a different set of examples here. All right, so here we have a mechanical system. It's made up of 2 different components, A and B, and they function independently of each other. Anytime we're told that things are independent in a question, we're assuming statistical independence there. All right, so the probability that A or B fail on any given day are 0.01 and 0.04 respectively. Now, if the system requires that at least one of these components is functioning in order to run, what is the probability that it breaks down on a given day? Okay, and so how does it break down, right? If we want to know, well, what's the probability that the event occurs, which is the breakdown, right? This is the same thing as saying, well, A has to break down and B has to break down. Because if only A breaks down, then it still works. If only B breaks down, it still works. And if neither of them breaks down, it still works. So the only way it breaks down is if both of them break down, right? But they function independently. And so we know that this is going to be the probability of A times the probability of B, because A and B are independent of one another. And as a result, we can take our probabilities here. So that's our 0.01 and our 0.04, right? And then we can plug those into our expression and get out the probability that the system breaks down on any given day. So system fails when they both fail. That is the A intersect B. Because of independence, we get probability of A and B is equal to probability of A times the probability of B. So that's 0.01 times 0.04, which gives us 0.0004. Okay. This only holds because we have independence. Now, what if this system requires that both of the components are functioning in order to run? What is the probability that it breaks down on any given day? And so we can think about this in sort of one of two different ways. In order for them both to be required, right, then we can say, well, if either A breaks down or B breaks down, then we'll have the whole system breaking down, right? And if you want to use an OR statement, that's A union B. Right, and if we think back to how we can do unions, that's going to be the probability of A plus the probability of B minus the probability of A and B. Right, and we have each of these different terms here. Right, we have probability of A is 0.01, probability of B is 0.04, probability of A and B is 0.0004, and so we can plug those into our expression here. Now, the other way that we can think about this is we could think about doing this through the complement event, right? So how does the system actually break down? Well, the system breaks down if either of them break down, then the system breaks down. And so how does the system continue to function? Well, the system continues to function only if A continues to function, which is A complement, and B continues to function, which is B complement, right? And so this is the only probability that that the system continues to function. And so we actually want 1 minus this probability, right? By independence, this is going to be 1 minus the probability of A complement times the probability of B complement, and we could plug in to get those values here, right? So either of these approaches is going to work for us here. And so we can walk through them to actually get out our numeric answers, right? We want probability of A or B. In general, probability A or B is going to be probability of A plus probability of B minus their joint probability. So that's 0.01 plus 0.04 minus 0.0004, which gives us 0.0496. Alternatively, we can take 1 minus the probability that both of them do not fail, right? So probability of A complement is 1 minus 0.01, probability of B complement is 1 minus 0.04, and so then probability of A complement and B complement is the product of those two, 0.99 times 0.96, so that's 0.9504. 1 minus 0.9504 gives us 0.0496. Okay, and so in this case, we're able to do that because knowing that A and B are independent also tells us that A complement and B complement have to be independent, right? And so we get the same answer no matter which approach we take here. So with independence so far, we've just been talking about two different events, but what happens if we have more than two events? So with more than two events, we need to differentiate between what we call mutual independence and pairwise independence. So a set of multiple events is said to be mutually independent if every subset of them of any size satisfies our independence assumption here. Okay, and so the idea here is that we have all of these events, E1 up to EK, and if we can pick out any arbitrary set of them, right? So we pick out E1 and E2, or we pick out E1, E2, and E3, or we pick out E3, E5, E7, right? Or we pick out all of them. If we can do this and always write this down broken up by the marginals, then they're said to be mutually independent. And so if you just have two events, right, you just have to check the subset of the two of them. But if you have three events, then you have to check. So for instance, if we have events A, B, and C, right, then we would need to check, is the probability of A and B equal to the probability of A times the probability of B? You would need to check, is the probability of A and C equal to the probability of A times the probability of C? You would need to check, is the probability of B and C equal to the probability of B times the probability of C? And you would need to check, is the probability of A, B, and C equal to the probability of A times the probability of B times the probability of C. Okay, so you'd need to check all of those different conditions. And if they all hold, then you would say that they are mutually independent. So checking for mutual independence can get really burdensome really quickly, right? But mutual independence is sort of a natural generalization of independence for two events. Okay. Now, Alternatively, we can also think about what we call pairwise independent. And events are said to be pairwise independent if any two events is going to satisfy our independence, right? So if you take out A and B, they're independent. If you take out B and C, they're independent. Or if you take out A and C, they're independent. Okay. If events are mutually independent, then they are also pairwise independent. However, if events are pairwise independent, they might not be mutually independent. And so mutual independence is stronger. It's actually a far bigger assumption than pairwise independence, and it's oftentimes going to be the assumption that we actually want. So mutual independence gives independence of every subset of events as well. So if a set of events are said to be independent, then if that's all we've said, we mean that to be mutually independent. But it's important to know mutual independence is quite a lot stronger than simply pairwise independent. So let's take a look at an example here. All right, suppose that a mechanical system is now made up of 3 different components, A, B, and C, and they all function independently. And so when we say that, we mean they are all mutually independent. The probabilities that A, B, or C fail on any given day are 0.05, 0.07, and 0.01, respectively. If the system requires that at least one of the 3 components be functioning in order to run, what is the probability that it breaks down on any given day? Right? And so here, in order for it to break down, we would need A to fail, and B to fail, and C to fail. But because these are mutually independent, right, we have probability of A times the probability of B times the probability of C. And then we can simply plug in our 0.05, our 0.07, and our 0.001, multiply those all through together, and then we're going to be given our answer, right? So that's going to be 0.05 times 0.07 times 0.001. It gives us 0.000035. Now, if they require all 3 components to be functioning in order to run, what is the probability that it breaks down on any given day? And in this case, it's actually going to be quite a lot simpler for us to work not with the union, right? Because we could think about this, just like in the two-way case, of we need this to be the probability of A or B or C, okay? And so we could work that out. But in fact, what we can also say is this is going to be 1 minus the probability of A complement intersect B complement intersect C complement, okay? And that's for the same argument before, right? The probability that the system continues to function is given to us only when A continues to function and B continues to function and C continues to function. And so then 1 minus that gives us the probability that it breaks down. And the reason that this is so nice for us is because we can write this now as 1 minus the probability A complement times by the probability of B complement times by the probability of C complement. Okay, and each one of those we can get by taking 1 minus 0.05, 1 minus 0.07, and 1 minus 0.01, respectively. Okay, and so then we can plug in here, right, and we get our calculation. Probability of A complement is 0.95, probability of B complement is 0.93, and probability of C complement is 0.99. And so then the joint product of them is 0.874665, and thus the probability we're looking for is 0.125335. Take a look at another set of examples here. So 2 fair 6-sided die are thrown. Take A to be the event that the sum is 7, B to be the event that the first die shows a 3, and C to be the event that the second die shows a 4. Okay. First, we want to find the marginal probabilities A, B, and C. And so A to be the event that the sum shows a 7, right? In order for us to look at this, there are 36 equally likely pairs of 6, or of dice, and 6 of them are going to sum to a 7, right? Because you can have a 1 on the first die with a 6, a 2 on the first die with a 5, a 3 on the first die with a 4 on the first die with a 3, a 5 on the first die with a 2, or a 6 on the first die with a 1, right? So 6 of them are going to sum up to 7, 36 total pairs, so thus the probability of A is 6 out of 36, or 1 in 6. For probability B and C, we can just look at our one single die, right? Because for B, we want the event that the first die shows a 3, so that's going to be 1 out of 6. For C, the second die shows a 4. That's also 1 out of 6. Right? And so what we have is that actually the probability of A, the probability of B, and the probability of C are all 1 out of 6. Now what we want to do is we want to find the joint probabilities of A and B, A and C, and B and C. Okay, and so what we can do is we can think about, well, how can they sum up to 7 if B shows a 3, right? So how can A happen if B has also happened? And in order for A and B to both happen, then what we need is that the second die is going to show a 4, right? So for A intersect B, we must have that the first die shows a 3 and the second die shows a 4. So there's only one combination there that's going to be 1 out of 36. for A and C to both happen, so the first die, or the sum is 7, and the second die shows a 4, we must have that the first die shows a 3, and the second die shows a 4. So that's 1 out of 36. For B intersects C, we must have that the first die shows a 3 and the second die shows a 4. There's only one combination out of the 36 possibilities. So all of these are going to be 1 out of 36. Okay? But now we want to find the probability of A and B and C. So what is the probability that A, B, and C happens? Well, the intersection occurs only when the first die is a 3 and the second die is a 4. So as a result, the three-way joint probability is 1 out of 36. So which events then are going to be pairwise independent? We know that the marginal probabilities are all 1 out of 6, the two-way joint probabilities are all 1 out of 36, and the three-way joint probability is also 1 out of 36. So A is independent of B because their product is the same. Their joint is equal to the product of the marginals. Same thing with A and C, and same thing with B and C, right? Pairwise, they're always independent. Are the events mutually independent? Okay, and so here we would need all of the pairwise, but remember we also have to check, is the probability of A and B and C equal to the probability of A times B times C? Is this true? Right, and so here we have this is 1 over 36. Here we have that this is 1 over 6 times 1 over 6 times 1 over 6. Okay, and so the answer is no, right? That's not going to hold. And that's because we're not going to have the three-way independence condition met. Okay, so probability of A and B and C does not equal to the product of the three. And so knowing any of A, B, or C guarantees the third. Right? If I tell you that both A and B have happened, then you know that C has happened. If I told you that B and C happened, you know that A happens, and so forth. And so in this case, we have a situation where we have pairwise independence, but we do not have mutual independence. Okay? So probability of A given BC, or probability of B given AC, or probability of C given AB are all equal to 1. Take a look at another example. Suppose that we have 3 fair coins and we're tossing them. A, B, and C are going to be the events of seeing a head on the first toss, the second toss, or the third toss. Okay? Are A, B, and C mutually independent? And so we would have to go through and actually check this. So we know that the probability of A, the probability of B, and the probability of C are all equal to 1/2, right? A intersect B intersect C occurs in exactly one configuration, right? And so there are a total of 2 to the power of 3, 2 times 2 times 2, sequences of 3 flips. And so 1 out of 8 of the time, the three-way happens, okay? As such, we do have that probability of A and B and C is equal to the probability of A times the probability of B times the probability of C. Now, A intersect B, A intersect C, and B intersect C occur exactly when heads appear on 2 of the tosses. Okay, and so we can work this out. That's always going to be 2 out of 4, or 2 out of 8 rather. So it gives you us 1 out of 4, right? And so in this situation, right, and just to dwell on that for 1 second, right? If we look at A intersect B, for instance, right, then what we know is that we need to have a head, and then we can get either a head and a tail, right? And so there's 2 ways that that can happen. If you wanted to look at A intersect C, then you know that you need a head, and then you can either have a head or a tail, and then you need another head. And so there's 2 ways that that can happen, right? And so for all of those, we get our 2 out of 8, okay, which gives us our 1 and 4. And as such, that's always going to be the product of the marginals. And so yes, these are all mutually independent. A, B, and C are mutually independent, and that should make some sense, right? The tosses of the coin don't actually influence one another. Now suppose that the 3 coins are tossed. We still have A, B, and C representing the individual heads events, but then D is taken to be the event that flips 1 and 2 match. And our question now is, are A, B, and D pairwise independent? Right, so we can work through our pairwise independence. And remember, for pairwise independence, what we'd want to check is probability of A and B equal to the probability of A times the probability of B. Well, we know that that's already the case because we checked that on the first pass, right? We then want to know, well, probability of A and D, is that equal to the probability of A times by the probability of D? And then we want to check, is the probability of B and D equal to the probability of B, times by the probability of D. So we need to check those two conditions here, right? And so A is independent of B from A, right? Probability of A is equal to the probability of B, which is equal to 0.5, okay, which we also have from A there, okay? For probability of D, there are going to be 2 of the 4 possible outcomes that have matching tosses, right? And so we have 2 out of 4, which are thus going to be 1/2, right? The other way that we can think about this, right? So we can think about this as being heads, and then we can have either a heads or a tails here, or we can have tails, and then either heads and a tails. And so you can either just think about the fact that there are 2 out of 4 on our first 2 tosses, or you can think about that there are 4 out of 8 on the total sequences, right? And so if you think about this as either being 4 out of 8 or 2 out of 4, it works out to be the same way, right? And that's whether you're considering the series of all of the tosses or the series of the 2 tosses, right? And it's up to you. It will work out to be the same thing. But either way, there are half of the time we're going to see that the first 2 tosses match, okay? And so then A intersect D occurs only if both flips are heads. And so then the probability of A and D is going to be 1 out of 4, right? So if you just flip the coin 2 times, right, 1 out of the 4 times, you're going to have 2 heads, which is the same thing as the probability of A times the probability of D. B intersect D occurs only if both flips are heads, right? And so you have probability of B and D is going to be 1 out of 4, which is probability of B times D. And so as a result, in all of these cases, we have our pairwise independence here, right? The pairwise independence holds. Every 2 of them that we pull out are going to be independent of one another. However, are they mutually independent? So A intersect B intersect D occurs only if both flips are heads, and thus the probability of A and B and D has to be 1 out of 4, just like the probability of B and D or just like the probability of A and D. And so this is not going to be the product of the 3 marginals, and thus they are not mutually independent. Right? So this is essentially the same thing as the previous example that we were looking at, right? Where we have pairwise independence, but we do not have mutual independence. Okay, and so it's important to work through the details there and make sure that that all clicks. But the sort of moral there is that just because we have independence of any pairs of events does not mean we're going to have independence of all of the events together. Statistical independence overall is going to be a crucial property. When we know that statistical independence holds, it really simplifies down our calculations, as we saw in those mechanical component examples, right? You can look at joint probabilities just by multiplying marginals. It captures an important truth that can be out in this world, right? So rolling dice, we know that they can influence each other, and as a result, we can sort of capture that statistically. However, it's really important for us to distinguish between pairwise and mutual independence. Mutual independence is much stronger. We can come up with examples, as we saw, where you have pairwise independence, but you don't have mutual independence. And so when we're thinking about multiple events, we need to be thinking, are these mutually independent or are they pairwise independent? And if they're mutually independent, everything simplifies very nicely. If they're only pairwise independent, then that's not going to be nearly as strong of a property for us, but we can still use that in certain settings.